two waves up, what is their interference pattern? Notice that some places give you destructive interference, some places give you constructive interference. Alright, let's stop at 105. It's a few more seconds, just guess if you're not sure. 105. See, a lot of people put A. A's not right. Let me show you. I know A looks right, because you get destructive interference right here, right? Because those two cancel out. And you get constructive interference right here, because those two add up. And so this is right here, and this is right here. Or this is right here, and this is right here. So really, it could be either A or D at this point. So now we need to look at this other part. Now you got three little parts to this. You got this part, the middle part, and the end part. So these two parts, destructive, right? One's up, one's down, they add up to give you nothing. Oh wait, no, A is right. I'm sorry. Ha ha ha. Alright. And then this part adds up with this part to give you destructive interference, so that gives you that. Sorry. Let me go back. Yeah. Sorry, D selectors. So I thought it was D too, so you're in good company, I think. Let's see, that wasn't really joke worthy, but since I messed it up, I'll give you one. And this, I wasn't going to tell you this one because it's crude and it's vulgar, and I think that you'll probably go away and you'll tell the dean, and then I get in trouble, and it's just a big old mess. It's not even really a joke, it's just sort of an interesting story about this guy that I knew once. He was like my algebra teacher. I sort of like, you know, he met with me and helped me study and stuff like that. The guy never, how am I going to say this without sounding crude? He never farted around other people. I mean, he was a private tutor. Sorry, I know that your view of me just dropped about 2 notches, but okay, this one's tricky. Let's try it out. When light waves travel a certain distance, they can get out of phase. And this is going to be a very important idea. So here what I have is I have a radio station. It's a very young ANS here. And it sends out radio waves. And it goes out, this is a mountain over by the bayou, that little hill. The radio waves, they go out and then they bounce off. So some of the radio waves go and then they bounce off, and some of them will just go straight to your home. And so you got two waves coming together. One has traveled a little bit longer distance, and the other has traveled a little bit shorter distance. And I want to know, what is this distance between the bayou and your home so that you get destructive interference? You need to ask yourself the question is, first of all, the wavelength of these waves is in the problem. The wavelength is 600 meters. And this distance is 50 kilometers. And so now I want to know, what is this distance if at this point I get destructive interference? If those two waves come together at my home and you get destructive interference. This does happen, by the way. Like, you can't have these sort of radio dead zones for this reason, where you have different waves coming together and they cancel out because of geological features. Some zones are radio quiet, right? Asia, you have radio quiet zones? Aren't you West Virginia? Yeah, West Virginia is like all radio quiet. Or parts of it are. That's why they have radio observatories there. All right, did I start the thing? Yeah. All right, let's go about 10 more seconds. So if you're not sure, just guess. I'll stop at 235. 235. Hey. What? It is a. Did y'all have the answer? Did somebody tell you the answer? Oh, you guessed. You all what?
Neither side just keeps getting in trouble.
Who? And then it spread throughout the whole place. Yes. Okay. All right. So, yeah, people usually get this wrong. So, in order to have your light rays have destructive interference, they need to be offset by a half wavelength. And so a half wavelength is equal to 300 meters, right? And so if I have a wave that travels a certain distance, and then I have another wave that I sort of hold it back a little bit, this distance right here is going to be a half wavelength. Notice it starts here and it goes over to here. That's a half wavelength. That's not a full wavelength. But when I hold back or when I shift over one of these waves by a half wavelength, then it causes destructive interference. So what I want to do is I want to have this wave travel a distance that's equal to a half wavelength longer. So how do we get 150 meters then? If a half wavelength is 300, like why isn't the answer B 300? Because what? No, that's a good guess. No, it has to be a half wavelength. Like the farther wave, the one on top, has to travel an extra half wavelength difference in order to get destructive interference. So why 150? Right, it goes twice. So it travels 150 meters extra, and then another 150 meters extra. This idea becomes really important going into the double slit, that when waves travel an extra distance longer, it puts them out of phase with other waves. It's the idea behind interferometers. You might have heard of interferometers, like LIGO, the LIGO interferometer up in Livingston. You know what I'm talking about? Sort of, kind of. Yeah, so that's the idea behind that interferometer. We'll talk about that in a bit. Okay, so how do we get these light waves that are coherent? Remember, coherent means that the phase doesn't change. Doesn't matter if it's in phase or out of phase, but that the phase doesn't change, that it's constant. And you also want light that's of constant wavelength, or the same wavelength. Today we'll do this with lasers. Okay? Where lasers, that's their real great feat, is that they produce this light source that's of a constant wavelength and that it's coherent. And that allows us to do all sorts of optical experiments. But before that, before we had lasers, which wasn't until like the 50s maybe, or 40s, 50s, the way that they got light that was coherent is that they would just use a light source, like a light bulb, or a lantern or whatever. The light that comes out of a light bulb is not coherent. That means that the light is all shifting around, the phase is all shifting around, it's not coherent. It could be of similar wavelengths, but not coherent. So if we don't use all the light, but we put a slit in front of it, so we're really only taking a very small portion of the light that comes from this light bulb. And so now when we take just a small portion of that light is coherent. Because I'm only taking a very small portion of the total light. Just a tiny little piece, and that piece is coherent with one another because it's basically from the same atoms that are creating the light. So those are coherent. And so that's been the way that we get coherent light sources prior to lasers. Now let's write this. So lasers also give a coherent light source. Coherent and constant wavelength. My grandfather invented the laser. Y'all know that? Actually, it was my academic grandfather. That's what they say. Like, you're my advisor's advisor, my PhD advisor's advisor. He invented the laser. Like, has it gone back up at all after that terrible joke? I didn't really have anything to do with the laser, but Charles Towns invented the laser. Let's watch a video about the double slit experiment, and then we'll get into this. Right, they could do the same thing that he did with the water waves. So they knew that waves interfered. They knew about interference, and they knew that with both mechanical waves and sound waves. But nobody had ever shown that electromagnetic waves did this, because they didn't think they were waves. Because we were sort of coming off Newton's era when everybody thought that light was a particle, and then some 100 years later or so, Thomas Young came in and sort of disturbed this whole idea. All right, so this was in 1801. You don't need to know the date, but just sort of give you some perspective. And this experiment demonstrated a wave-like property of light. All right, and where we get constructive interference is where two waves meet up, where their peaks and peaks line up and their troughs and troughs line up. And where we get destructive interference is where two waves line up, where their peaks and troughs line up like that. So you get one bright spot right here, where the amplitude is increased, and then over here you get no spot at all. You get a dark spot. The light just goes away. This is largely, or it is due to different distances that they travel, and we'll derive that. I'll show you how that comes about. So it's actually not that difficult to look at how we derive this geometrically. I have two slits. They're separated by a distance d. That'll be one of our variables, actually. Actually, let me go ahead and write down the expression. I'll write it again later. But the expression for a double slit that Thomas Young came up with is d sine theta m lambda. And d here represents the angle between the two, or not the angle, the distance between the two slits. These are usually pretty close, on the, tenths or hundreds of millimeters, not very far apart. The angle then is this angle right here. So it's the angle at which they meet at on the screen. So you can have an angle of 0 degrees, for example, like this would be theta equal to 0 degrees. And then you can imagine that over here, theta would equal to 90 degrees. So a 90-degree angle actually isn't going to show up on the screen, and we'll come back to that when we get to diffraction gratings. But our angle can go from 0 to conceivably, possibly, up to 90 degrees. Now, notice that a light wave starting here will travel a certain distance, and then this light wave travels a slightly longer distance, and so this is that longer distance. And we can calculate what that is just from geometry, because I got this triangle right here, which is the same as this triangle, and our path length difference, which is called PD, is equal to d times sine theta. Now there is some assumption there that your angle theta is a small angle, but that's okay, we'll go with it. So that's where our path length difference is equal to d sine theta. So in this expression, d sine theta is the difference in the path lengths between the two rays. And depending on what that difference in path length is, will tell us whether we get destructive or constructive interference. If the path length is equal to a half a wavelength, I'm going to get what kind of interference? Constructive or destructive? I get destructive. So if I have a half wavelength, if my path length difference is a half a wavelength, that gives me destructive interference. If it's a full wavelength, then I get constructive interference. And if it's somewhere in between, well, it's somewhere in between. So what I would have on my screen here, let's see, I'll do the bright spots as blue. I'll do them as red. I'll do them as yellow. I'll do them as yellow. So there's a bright spot, bright spot, bright spot, and then they're symmetrical, so I get a bright spot over here and a bright spot over here. And then in between, I get dark spots. Dark spot, dark spot, dark spot, dark spot. Now, often we'll express this as a graph, and the graph will look something like this. Something like that. Because this is, you saw in the video, this central spot, because this is total constructive interference. There's zero difference between the path lengths. This is the brightest spot. This one's still bright, but it's like I'm shifted over one wavelength. So it's constructive, but it's not complete constructive interference. And then over here, I shift over another wavelength. So I'm losing some light, but I'm still getting constructive interference. So here in the middle, it'd be like this. Right here, I would shift over one wavelength, because I have one wavelength path length difference. And then the third bright spot, I'd shift over another wavelength, and then another wavelength, and eventually the dots go away. And we'll talk about that later. So I use this graph to represent the intensity of the light. So if the graph goes up higher, then that's where the brightest spot is. Okay, so for constructive interference to occur, the two rays must be in phase. And for the central maximum, the difference the rays travel is zero. Or I can think of it as zero wavelengths. So total constructive interference occurs. By the way, I'll go ahead and write this. I'll write it again later, but let's go ahead and address it here. That here, for this simple bright spot, my path length difference is zero wavelengths. Here, it's one wavelength. Here is two wavelengths. And then in between, I have a half a wavelength, I have 1.5 wavelengths, I have 2.5 wavelengths, and on and on. So I alternate between dark and bright spots as my path length difference increases by a half a wavelength. So then the first bright spot next to the central occurs when the two wavelengths are offset by how much? That sort of neighboring bright spot, I'm offset by one wavelength, right? And the path difference is given by this d sine theta. So the position of bright spots is given by this d sine theta equals m lambda. And here m is called the order number. And it has values equal to 0, 1, 2, 3, and on and on. It doesn't go on forever because eventually the orders go away. But they'll increase in increments of 1. 0 plus 1 plus 1 plus 1. Okay? Note that this gives the bright spots. I think on your equation sheet it says bright spots. It's only important because later we'll see a very similar equation that's for dark spots. Sometimes I use spots. Also, sometimes we'll see the word fringes. So don't be confused by that. Let's go ahead and write that these words are identical. When I say spots or fringes, that refers just to the bright or the dark spots. Spots and fringes, that those are equal. Okay, so similarly, destructive interference, when the path difference in the waves is a half a wavelength out of phase. So d sine theta then is m plus 1/2 times lambda. That's all that's saying. So my first dark spot occurs at m equals 0. That would be the path length difference is a half a wavelength. The next one occurs at m equal 1. That's 1.5 wavelengths, 2.5 wavelengths, 3.5 wavelengths, and on and on. So let me redraw this. We've had this before, but this is the screen, and this represents my interference pattern. All right, so this is m equals 0. This is m equal 1, and then this is m equal 2. And if you had a third, that would be m equal 3. And by the way, it's also symmetrical, so this is 1, 2, 3. We don't use negatives. And then the dark spots, we don't have order numbers in this case for the dark spots, although it's going to be different for single slit diffraction, but very similar. But you can imagine that the path length difference here is a half a wavelength. The path length difference here is 1.5 wavelengths. That's where that m plus 1/2 comes from. So this would be m equals 0, and this would be m equal 1. Follow what I'm saying here? On my dark spots, my first one occurs when m equals 0, right here, and that gives me a path length difference, d sine theta, equal to a half a wavelength. You'll need to know how these work out, because you'll have a couple questions about this. I'll ask you, what is the path length difference here? Or how many degrees is it out of phase? Those sorts of things. We'll see that in practice next time. One more thing, and then I'll let y'all go. So if I have my screen, it has my interference pattern on it. Here's my double slit over here. Let's say that I'm going to my second order bright spot. This is m equal 2. And I want to know what is the distance between here and here. That's y. I'll call this distance L is the distance from the screen to the double slit. And then this is my angle theta. That's the same angle theta that's in d sine theta. So I can calculate what y is, because I know that, tan of theta is SOHCAHTOA, opposite over adjacent. That's y over L. So I can calculate y is going to be y equal to L tan theta. Sometimes I'll want to know the distance between dark or bright spots. In order to do that, I use this trig function to find y. That's also on your equation sheet, so don't bother memorizing it, but it just comes about from that tangent function. Hold on just a second, let me see. I think that might be a good stopping point, but hold on, where are we at? Yeah, we'll pick up. No, let's do this. We can do it. We have 30 minutes. I need 3 minutes.
3 minutes is not enough time.
All right. Y'all have a good weekend, okay?